Hello, welcome back. Let's talk about section 11.2, second derivatives and graphs. Okay, so for this problem, we want to inspect the graph of the function, determine where it's concave up, concave down, or neither on the given interval. So we have a cubic function. It's like an upside down and stretched cubic function. And we're only considering negative infinity to 0, so it's really this piece. Just keep that in mind. All right, and so concavity can be determined by, and maybe this is suggested by the section title, but concavity is determined by the second derivative. So to get the second derivative, we need the first derivative. So let's find m prime. We can just use the power rule and get 9x squared. And now we need our second derivative. So that's just taking the derivative of the derivative. So that gives me negative 18x. All right. And so similar to what we did in the last section, we want to know where the partition points are now of my second derivative. So where my second derivative is 0 or where it doesn't exist or not defined. It is a straight line. Looks our second derivative. Looks something like that, maybe a little more extreme. Okay, so it's defined everywhere, so this will never happen. But we can find that it is 0 when my x is 0. So that forms the partition 0 and kind of works out that we're only considering from negative infinity to 0, so we don't even have to look at a number to the right of 0. So let's just test what my m double prime is of negative 1. So m double prime of negative 1, we plug that in to our negative 18x, and I get a positive number, right? Positive 18. So that means that my second derivative is positive, and so that corresponds to my original function, my m of x, being concave up. All right, so our answer is concave up. If my second derivative were negative, then it'd be concave down. But I'm sure we'll see more examples of that. So now we have a different function, n of x. Let's rewrite n of x because I don't like dealing with square roots. So I'm just going to use this little power trick. Make the power 1/2. That's the same thing as square root. And again, same kind of interval. And so let's take our first derivative. So power rule 1/2. Bring that 1/2 down, minus 3x to the minus 1/2, and then chain rule because I have a function on the inside. So minus 3, so I get minus 3 over 2, minus 3x and minus 1/2, and that's our first derivative, but we actually need the second derivative. So let's take the derivative again. Bring that on the outside, bring the power down, and then decrease it by 1, so that'll give me negative 3/2, right? Negative 1/2 minus 1 is the same as negative 1/2 minus 2 over 2, which is just minus 3 over 2, so that's how I get this power here. And then chain rule, right? Again, another chain rule. So all in all, I get 9. Let's see, do I get a positive? I get negative 9, right? There's 3 negatives all being multiplied, so that makes negative 9 over 4. Negative 3x to the negative 3/2. And we can rewrite it to make it look nicer for the next step. We can rewrite it as the square root of negative 3x to the third power. All right, and that's our second derivative. So now we want to know what the partition points are. So n double prime is equal to 0. This will be never, because we have a constant in the numerator, so my numerator will never equal 0. And so my second derivative will never equal 0. But my second derivative is undefined, and that's occurring when my denominator, 4 square root of negative 3x all cubed equals 0, right? When I have a divide by 0 error. So we can simplify this a little, move the 4 to the other side and square root it, which still gives me 0. Or square it, and then we take the cube root to undo that, right? Again, I still have 0. So negative 3x equals 0. So really, 0 is our partition point, which kind of works out. Remember, I only want to know to the left of 0. So let's plug in negative 1 into my second derivative. So negative 1 into here. Oops, let me put a negative 1. So negative 3 times negative 1 actually gives me positive 3, right? So this will be positive 3. But since I have a negative over here, this actually will all be a negative number, whatever it comes out to. So no, you don't actually have to find what the value is. It's more about the sign. And so when my second derivative is negative, that means that my function is concave down. So now you've seen both cases where concave up is when your second derivative is positive, and then when it's negative, it is concave down. Okay. So let's look at this one. We want to match these conditions to the given graphs. I don't think we've ever seen a problem like this, but anyway. Let's see. So I think the best route is just to describe these characteristics in terms of f. All right, so f. So when my first derivative is positive, that means my my f is increasing. Same for this one, right? F is increasing. Here my f prime is negative, so that means my f is decreasing. And same for 16, f is decreasing. Okay, and then now let's look on this other piece. My second derivative is positive, so this means and concave up. Right, this next one, my second derivative is negative, so this means I'm concave down. And then similarly, concave up and concave down. Concave down. Okay, so now let's match it. So I'm going to match 13. We were looking for something that's increasing and concave up. So this is increasing, concave down. This is increasing, right? Left to right. And it's concave up, right? It kind of looks like a bowl. If you filled it up with, I don't know, milk or something, it wouldn't spill out. Whereas in A, if you filled it up, I guess it would like spill out this way. I don't know. Whatever you like to visualize for concavity, just roll with it. But our answer is C. Okay. Our 14, we want an increasing function in concave down, which we kind of hinted to it, but we're increasing here and then it's concave down, right? It's like an upside down bowl, I suppose. So this one is A. So for 15, we want a function that's decreasing and concave up. 16 is decreasing but concave down. So between B and D, which one's which? Well, B looks like to be concave down, right? That upside down bowl. So that is 16. And then D is our last one, but this looks concave up, so that's 15. Okay, so here we just need the second derivative. So let's take the first derivative of f. So yeah, we can break it apart term by term because of the sum difference rule. 36x to the third, right? Power rule, minus 8 times 2 is 16. Decrease the power, plus 8. Okay. And then the next one is f double prime. So I want 36 times 3 for the power rule, x squared now, minus 16. So this is 103 x squared minus 16. And that's our second derivative. Okay, for this next one, we have it's 4x to the minus 3 minus 7x to the minus 8. So again, we can separate it. Let's find h prime first. So separate each term, and we're using the power rule. So minus 3, bring that power down, x, and then decrease the power by 1. Same thing for the second term, so 7, bring the power down, x, 8 minus 1. All right, so for this one, just be careful of your negatives. They appear a little more often in this one, so let's just be careful. 56. All right, that's what I got for my first derivative. So let's do it one more time. Take the derivative of the derivative. It's pretty much the same process, just different numbers now. Minus 56 times minus 9x, and then decrease that power. So I get 48x to the minus 5th power, minus, that comes out to 504. X to the minus 10th power, and that is my second derivative for each of x. Okay, so in this one, we want to know what our points of inflection are, inflection points. So these are where concavity changes, right? Where we have, when we go up to down, or down to up. All right, so I mean graphically, up to down would mean maybe something like this. And so my inflection point would be here. And then concave down to up may look something like that. But anyway, we can find these algebraically. But remember, we're talking about concavity, so this means second derivative. Pretty much the whole thing we're doing for the section anyway. So f prime, let's find that first. That's just going to be 3x squared plus 21 times 2 is 42x. So that's my first derivative. All right, and then my second derivative, do it one more time, 6x plus 42. And so inflection points occur, or potentially occur, when we have partition points, like on our sign chart, and then concavity changes. So we'll need our partitions of f double prime. So that's again where it's 0 or not defined. Our derivative, our second derivative, is a polynomial. It's a line, so this is never. But let's find out where it's equal to 0. That seems to occur, at -7. So I have this on my line, and now the last thing I need to know is, does my concavity change before and after -7? So remember how to do that. We plug in points. We can find these test points and plug in a point to the left and right of it. So I want to find f prime of -8, and just to focus on the sign. Right, so 6 times -8 plus 42, that's going to give me -48 plus 42, which is a negative number, right? -6. and f prime of 0, so 6 times 0 plus 42, that'll give me positive 42, so positive number. So does our concavity change? So f prime goes concave. So when my f double prime is negative, that means I'm concave down. And when we're positive in our second derivative, that means we're concave up. So our concavity does change, and so -7 is a point of inflection. And A is our answer. Okay, let's do one more. Now we have a slightly, maybe more difficult, but I believe we can do it. So let's first find our first derivative. So just be careful because we have fractions now, so you can use parentheses and just take your time with it. So to take that derivative, I brought the power down. Now I'm going to decrease it by 1. I'm just going to write it as 5/5 instead of 1. Okay, and this simplifies to 27/5 x to the 4/5. And I said I am going to need it in my second derivative, so let's take that as well. Bring that power down, x, and decrease it by 1. Again, I'm going to write it as 5/5 just because it's fractions. So this gives me a derivative of 108 over 25, x to the -1/5. Or you can also write it like this if you want. So this is the 5th root of x in the denominator because this is a negative power. Okay, so again, let's find our partitions of f double prime. So f double prime is equal to 0, never, right? Our numerator is never going to equal 0, but our denominator will. And where will that occur? So f double prime does not exist or not defined when 25 times the 5th root of x is equal to 0, 5th root of x is equal to 0, or where x is equal to 0, right? 0 to the 5th. So pretty much 0. So let's check if this partition now, x equals 0, is a point of inflection. So again, let's use these test points, -1 and 1. I'm going to plug them into my second derivative because we want to know what the sign is of it. So f prime of -1. So let's use this form down here. I have 108 over 25, the 5th root of -1. Well, the 5th root of -1 will be a negative. It'll be -1, so this will lead to a negative number. And then if we find f prime of +1, this will lead to a positive number, right? There's no negatives. So see how you don't necessarily need to compute it if you're careful about your signs, but if it's easier for you to compute it, go ahead and just see what sign it is. So when my f prime is negative, or double prime is negative, my f is concave up or down? Down, right? And then when it's positive, I'm concave up. So my concavity does change, and so 0 is a point of inflection. Okay, so that's how we do that problem. Let's look at a new type of question. Here we have the sign chart. This is the sign chart for f prime, and then we have the sign chart for f double prime. We're also given some function values, these x values, if we care to know, but personally we could probably figure it out between the two sign charts. So I'm going to use our sign charts and kind of extract information from them. So let's start with the first one about f prime. So when my f prime, it's positive on this interval, right? So when my first derivative is positive, that means my f is increasing. And on what interval? Well, that's from negative infinity to negative 3, right? Wherever I see plus, plus, plus. And then conversely, notice that we're negative in between here. So that means my f is decreasing on the intervals from negative 3 to 3, and then 3 to positive infinity. All right, so that's a few pieces of information we can get from our first sign chart. Now let's look at our second one about the second derivative. So my second derivative is positive in between negative 1.5 and 3. So then that means my function is concave up or down. It will be concave up, and this will be between, again, those partition points. And now let's look at when my second derivative is negative. That's this, or these intervals. So my function is concave down when my second derivative is negative. So these form the intervals here. And so now let's kind of glue it all together. I'm sorry, that should be a infinity. Let's glue all these pieces of information together and try to figure out which graph f is. So f is increasing up until negative 3. And again, I want to say 1, 2, 3, 4, 5, 6, 7, 8, 9. So each tick mark is 1. Thank goodness. Okay, so let's look at negative 3. Negative 3 is right here. Well, this one can't be it, right? Because I see that my function's decreasing here, but it needs to be strictly increasing. For the same reason, it's decreasing here before we even get to negative 3. So that's why we can throw an A and B out. We can see that C and D do increase up until negative 3. So that's good. What else? It's decreasing everywhere else. Yeah, that's true, right? Maybe except for 3 where it would be 0, potentially. Let's see. This right here, and I kind of drew over it. This is 3 right here. Notice that my tangent line is not exactly horizontal, whereas here it is. So that might be a sign that D is probably more likely the answer. Let's look at concavity while we're at it. So we know that we're concave up between 1.5 and 3. But look at part C. It looks like there's a little piece maybe here where we're concave up. Whereas over here, it seems the concavity stops when we get to 3. And so I think we should go for D for this question, right? Let's throw out C. Okay, it's kind of hard to tell, but zoom in and just make sure that you match it up with what you know and what's given. I suppose you could also match up these points and see if they line up. Okay, let's try another one. So kind of the same, just it looks different, right? It's basically the same information or type of information. We have 2 sign charts and values, and it's just presented differently. That's odd. Okay, so let's do the same thing. I'm going to look at my sign chart for f prime, and this is going to decide whether my function's increasing or decreasing. So I notice from here, oh, they highlighted it. I didn't even realize that. So in the highlighted blue areas, our f prime is positive, so that means my f is increasing on the intervals from negative infinity to these partition points. 0 to 2, and then 5 to infinity. And then now we can look at the gray part of my sign chart. So this means that my f prime is negative, which means my f is decreasing on 2 to 5. So now let's look at our second sign chart. Again, where it's blue is where my second derivative is positive, and that translates to where my f is concave up. So that will be from negative infinity to 0 and 3 to positive infinity. And then similarly, let's look at when we're concave down. That will be my gray piece of the second sign chart. And that's between 0 and 3. So now let's see, if we can pick which function it is. So let's start with our first criteria. F is increasing from negative infinity to 0. So right off the bat, we're decreasing here, right, from negative infinity to 0. So A is not it. Kind of the same reason for B, right? We have a decreasing function basically up until here, which does not match our description. So let's throw out B. C, we are increasing up until 0 from left to right. So possible answer. And then D, we are increasing, but then we start to decrease at, I don't know, 1.5, negative 1.5. Anyway, so D is our answer. And we didn't even have to look at the other criteria, but I mean, we can continue if you'd like. So it's decreasing from 2 to infinity, right? I'm sorry, we should also look at 0 to 2. So it is still increasing to 2, which I'd imagine is somewhere there. And then we're decreasing from 2 to 5, which I imagine is this piece. And then we're increasing again. So that matches the description of our increasing and decreasing parts. Let's look at concavity. So we want to be concave up from 0, or from negative infinity to 0, which we are, right? It looks like a bowl that's upright. And then we also want to be concave up from 3 to infinity. So that also looks like it's standing upright. And then concave down in between. And yeah, that fits the description, so C is our answer. Alrighty, so here we want to use a graph. So now this is f prime, so this is our first derivative. And we want to look at where f is decreasing, f is increasing first. So when my f is decreasing, what does this mean for our f prime? Well, this means that our f prime is going to be negative or less than 0. And then when f is increasing, that means my f prime is going to be positive. So since we're looking at the graph of f prime, we want to know what part or what intervals for which my f prime is positive or negative. So this is really, is it below the x-axis or is it above? And that's how we can answer this question. So f is decreasing, that means that my f prime is below the x-axis. So that's this piece, right? It's all negative. So this is not f, this is f prime. And so, geez, what is the scale on this one? Let's see, so that's 10, so I'm guessing each tick mark is 2, so I'm going to say -6 for here, right? -6 right here. That seems to be one of the partitions, so -6, and then let me track it, it's negative, and then right here at 12, f prime of 12, it actually hits the x-axis, so it's going to be 0. So you have to write the answer this way and exclude 12. Because if we were to draw a sign chart, right, you would have 12 as a partition and 6. And then you'd put zeros, right, because they touch the x-axis. So that's why you would not include it in our interval for the first question. Okay, so that's our intervals for the first part. And then the second part is just the leftover piece that's positive, right? My f f prime is positive from negative infinity to negative 6. Okay. So now, oops, let me hide that. So now we want to know where f has a local min and where f has a local max. So remember that this is f prime, and we had the sign chart of our partitions of negative 6 and 12, and then it was negative, 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 and positive, positive. F prime, so this means that f is increasing, decreasing, decreasing. And so that means from negative 6, we're going up, up and then down, right? Increasing, decreasing. So that means negative 6 is a local min or max. So it will be a local max at negative 6. I might have said positive 6, but I meant negative 6. And then for 12, we're decreasing before 12 and also decreasing after 12, or some sort of decreasing. So we don't have any sort of local min. Okay. So we want to know where f is concave. Let's see, downward, right? Downward. Okay, so this means where is my derivative, the derivative of the derivative, going to be negative, right? So it's my, let's see. So my f double prime, when it's negative, right, my f will be concave down. Down. Okay, and so in relation to our first derivative, when f double prime is negative, that means that my f prime is decreasing. So we want to know on what intervals is f prime decreasing. So if we look at our graph, because luckily we have that part, we're decreasing on these intervals. Here from negative infinity to 0, and also from 12 and on. So our answer to this question is negative infinity to 0 and 12 to infinity. And then for concave up, it's just the opposite, right? So my concavity is going to be upwards, so it's going to be positive. And this means my f prime is increasing. Right, and then f is concave down, concave up. All right, it's a little messy. Okay, so now we want to know where my f prime is increasing, and that is this piece, right? Between 0 and 12. And so we notice between our two answers here that concavity changes at these points. Let me maybe in green. My concavity goes from concave down to concave up, and then concave up to concave down. So that's why we have two inflection points at 0 and 12, x, right? Those are those green points. So if we put all this information together, we have enough information to graph f, right? So we know that f is decreasing on this interval. So let's see, from negative 6 to 12, but f is increasing before negative 6. So that's why A, which is decreasing before negative 6, is out. Same for B, no good. But C and D look good, right? We're increasing, increasing. What about D? Let's look at D. So I want to be increasing from negative infinity to negative 6. And I think 1, 2, 3, 4, 5, 6. So each tick mark is 4. So this is -4, -8, -12. Sorry, it's kind of hard to see, but we notice that we are decreasing for some amount before -6 on D. So C is most likely our answer, but we can confirm looking at our other information. So we are increasing from -infinity to -6. Then we are decreasing from -6 to 12, which is about here, 12. And then I notice I have a horizontal tangent at 12, which is good. And then we're still decreasing, so C does fit the description pretty well. We also have a local max at -6, right? This is a local max. Let's see, concave downward, right? Kind of looks upside down bowl-ish to me from here and here. And then right about here and here, which I imagine is 0 to 12, that looks like concave upwards. So C is our answer for this question. All right, let's do this problem. Second to last problem for us tonight. Okay, so we use the graph on the right, which is our f prime. All right, and we want to know what's happening with f. Okay, so let's just do this column first. I think that'll be good. Okay, and I know it's not shown here, but these drop downs are either like positive or negative for these, increasing, decreasing for these. And then these middle boxes right here is about extrema. And then here it's increasing, decreasing. This is about concavity. Oops. Cavity, up or down. And then this is points of inflection. So it'd be more clear on your screen. But I'm just putting this here for now. Okay, so all right, so in different intervals. So for this column, let me highlight it here. We'll do these first because this one's relatively easy. We want to know the sign of the f prime. So if we look at our graph, it actually lives entirely above the x-axis, right? And then it kind of touches it here and there, right? These 2 points, but that kind of leads us to believe that all of these are going to be plus, right? And when my f prime is positive, so when my f prime of x is positive, that means that my f is increasing. So that's why all of these are going to be increasing. So it's actually not too bad. All right, so we just got rid of all those. Woohoo. Okay, so next, let's look at f prime, whether it's increasing or decreasing. Let's do that one next. Okay, so f prime, our first interval, we want to know from -infinity to -5, and I believe this is -5 where they touch the x-axis, and that's +5. So those are our partitions, right? Where f prime is equal to 0. But anyway, the first interval, our f prime is decreasing, right? Left to right. And so when our f prime is decreasing, that means that my f is concave down. So concave down. All right, let's look at our next interval. I have from -5 to 0. So that's this part right here. And so that's increasing, right? Our derivative is increasing. And so when f double prime is increasing, that means my f is concave up. So that corresponds to this blank being concave up. All right, and then same thing for the next interval we're looking at, 0 to 5. So we look like our f prime is decreasing. And then we stated that this corresponds to concave down. And then for our last interval, our derivative is increasing. And so what does that correspond to? Concave up. Okay, so let's answer our last blanks. So for this first column, we want to know what the extrema of f prime is. So at x equals -5, -5 is a local minimum, right? Local minimum of f prime. And let's look at x equals 0. That's a local max on our graph of f prime. And then again, +5 is going to be a local minimum of f prime. Right? And then, and our very last column, I suppose, we want to look at inflection points. So inflection points, again, are where concavity changes. And we can kind of see that basically all of these concavity changes, right? Concave down to concave up to concave down, and concave down to concave up. So these are all inflection points. I'm just going to abbreviate. So that's our filled in chart for this one. Okay. Hopefully that made some sense to you. Just talking about f prime given our graph and then what that means for f. And so now we're going to use all that information and try to plot a potential or a likely graph of f, right? And so we can focus on this one, right? So we're increasing everywhere, right? That's what this whole column's telling us. So A is decreasing, right? Decreasing everywhere, same for the B, decreasing. So we can throw them out. Next, let's look at concavity. I think that'll be a good one. So from -infinity to -5, again, I think these are, each check mark is 1. So 1, 2, 3, 4, 5. So this is -5. We are concave downward. No, right? That looks kind of concave up to me. So perhaps D is it. 1, 2, 3, 4, 5. Yeah, look at that. That looks concave down. So that kind of checks out. Concave up from 5 to 0. Yeah, that looks concave up. And then concave down, again, upside down bowl, and then right side up bowl. So D is going to be our answer for this one. All right, let's do our last, application-based questions. So, or second last, I suppose. So one commonly used measure of inflation is the annual rate of change of the consumer price index. So a news story says that the annual rate of change of the CPI is increasing. So what does it say about the shape of the graph of CPI? So it's saying that the rate of change, so we can almost call it like CPI prime, is increasing. And so when CPI prime, or we can think of it as F prime, is increasing, this means that my F double prime is positive. And then in terms of F, this means that F is concave up, right? So we can just replace F with our CPI if you'd like. F prime is increasing, CPI oops, CPI is positive, I can't spell, and then CPI is concave up. So that is A. All right, let's do one last problem. So we have a graph C of X. This is our total cost in dollars. And we want to know what the graph of the marginal cost function C prime is. So looking at our graph, C prime of X is increasing everywhere. So that means that, I'm sorry, my C is increasing everywhere. So that corresponds to C prime of X is positive everywhere. So that's good. Also, C of X, my graph is kind of showing a concave downward. So this means that my C prime of X is decreasing, right? Because concave down means C double prime of X is negative, which these two mean the same. So in terms of C prime, we want these two characteristics. And so I think the only one that has it, right, they're just different combinations of positive, negative, increasing, decreasing, is actually A. And that's how we answer this question. Okay, so that concludes 11.2. So yeah, I hope this was helpful. We'll see you for 11.4 when we talk about curve sketching techniques.